The goal of Group Two's project was to predict the team rankings of the NHL playoffs. The National Hockey League spans 32 teams across the United States and Canada. In a normal season, each team will play 82 games, meaning 2,624 games total. This leads to a huge amount of data and statistics generated per season. Although quickly gaining popularity, there has not been much interest in predicting playoff spots for the NHL, especially with utilizing machine learning models. The Stanley Cup playoffs consist of 16 games. Our objective was to not only build a classifier that could identify the 16 teams that would make it to the playoffs, but also find the order of the rankings of the teams given data from only the first half of the season.
Our dataset was sourced from Kaggle and is comprised of 9 different tables tracking various NHL metrics, which include goals scored, penalties, saves, and even play-by-play data. These tables were trimmed to only include numerical data, the first half of the season, and seasons that were shortened due to COVID and labor lockouts, to make our playoff predictions. Furthermore, we manually tabulated the top 16 teams for each season from online to serve as the labels for our classifier. From there, 2 main datasets were built. The first was smaller and gave an overall summary of the team's performance consisting of average statistics for each team. The second was larger, and rather than looking at team performance as a whole, this dataset consisted of data from each game. On the left, you can see a block diagram of the various tables that were found in Kaggle. The season summary data consists of data such as wins, goals, and shots for every team, and the labels we are trying to predict are the final standing of the team. The game by game consists of data such as shots, hits, and injuries for every game, and the labels we are trying to predict are the outcome of the game. However, an issue arises when we look to predict game outcomes for the second half of the season. Due to the fact that we are only using data from only the first half, we do not have game data in the second half. Thus, game statistics were generated from 2 tables. The first table is a summary of a given team's performance in the first half of the season. The second table is a summary of a given team's opposition's performance in the first half of the season. By averaging these two given a team matchup in a game, the second half season game data could be generated and the game outcome predicted.
The methods we used included feature reduction with PCA, as well as various different logistic regression and naive-Bayes models. For both, we created a binary class and a multi-class model. For the logistic regression, we also implemented our unique game-by-game approach. For dimensionality reduction, we decided to implement PCA for our project. Before running PCA on any of our datasets, we had to find the correct number of components to reduce down to. To find this, we plotted the variance against the number of components. And as we can see on the graph here, we found the number of components that corresponded to around 95% variance.
For our binary classification models, we used summary data for the first half of the season, so this was data until January. Our approach was to put each team into 2 classes, whether they made the playoffs or not. This required us to change the data a bit so that there was a 0 in the data if the team did not make it to the playoffs and a 1 if they did instead of their ranking. To predict the ranking of the teams that made it to the playoffs, we used the probability of the team being in class 0 or 1.
For our naive Bayes and logistic regression multi-classification approach, we use the same data set that we used for binary classification. The idea here was that every playoff standing would be its own individual class. To emulate this, we assigned 0 to all of the teams that did not have playoff standings. This gave us 17 classes, of which 16 were actual rankings in the playoffs, and 1 was for the teams who did not make it. The advantage of this approach over binary classification is that the rankings are calculated directly without having to create them manually.
Our last logistic regression model was the game-by-game approach. As mentioned earlier, training and test data was split within each season to predict game outcomes of the second half of the season. Thus, training data consisted of first half games, stats, and outcomes. Testing data was pairing of second half matchups with predicted corresponding stats regarding opponent history. The model's predicted second half game outcomes can be used to calculate total win counts for all teams across all seasons. Total win counts can then be used to extract the 16 teams that make playoffs.
Now we'll discuss the results of each model. We first created a logistic regression model using binary classification, as this was a more conventional way to use this model. We had 2 different versions using a dataset with less features and another with more. They performed very similarly to each other with an accuracy of 71 and 74% respectively, regarding if a team made it to the playoffs or not. Our next step was to predict the rankings. Here are the rankings we predicted using the probabilities of each team making it to the playoffs. In this scatter plot, we would hope to see that there would be a steady decline in probabilities as the ranking increases. However, as you can see, this is not the case. The rankings seem to have little to do with the probability. The accuracy of our predicted rankings was 36% for the dataset with less features. This model with more features was able to get a few more of the rankings correct, but still not as accurately as we had hoped. No clear relationship between the probability and true standing can be seen. The accuracy of our predicted rankings was set 45% here. Since the goal of our project was to predict the rankings, we decided to create a multi-classification version of logistic regression, as this would allow us to directly predict the rankings. As expected, the accuracy of this model was incredibly low at 32%. Also, the ROC curve looks nothing like what is expected for this type of model. Building this model allowed us to realize that 17 labels is too many for the model to perform well.
For the game-by-game logistic regression, multiple measures can be analyzed due to the nature of the training and testing split being within each season. On the left is the ROC curve respective to predicting second-half game outcomes across all seasons, which has a 50% accuracy. On the right is the accuracies of making playoffs, not respective to rankings for every season. Note, the 2018 season that every other model looks at for accuracy is 68% here. Accuracy plummeted from 68% to 35% when not only predicting making the playoffs, but also the ranking.
Our naive Bayes binary classification reached an accuracy of around 48%, but it is worth noting that that accuracy mainly comes from the model correctly predicting teams that did not make it to the playoffs rather than teams that did. Our naive Bayes multi-classification did worse than the binary classification because it had not 2, but 17 classes to choose from. This gave the model many more incorrect options to choose from, resulting in a lower accuracy. Here, it is the same scenario where the model correctly predicts teams that don't make it to the playoffs rather than the correct rankings.
Here's a table of the accuracies from each model we created. As you can see, the model with the highest accuracy was naive Bayes with binary classification. This binary classification model was able to most accurately determine whether a team made it to the playoffs or not. The naive Bayes multi-classification model and the logistic regression game-by-game model performed the worst with an accuracy of 35%. This was expected due to the fact that there were 17 classes in this approach, and the number of labels significantly decreases the accuracy of a model. Overall, the naive Bayes models perform better on average than the logistic regression models. Because of this, we believe it is safe to assume that our features are close to conditionally independent. One of the reasons that our naive Bayes model outperformed our logistic regression models is the nature of discriminative and generative models. Although discriminative models outperform generative models in the long run, in the case of fewer training datasets such as our own, the generative model reaches a higher accuracy on average. Looking back on our project, we believe that our accuracy could be improved with more training data and tuning the features in our dataset. By introducing new features that are helpful to our model and removing features that are just noise, we can improve our accuracy across the board. When it comes to having more training data, we recommend introducing more data from the season we are predicting on, as opposed to data spread across multiple seasons. Another thing we could do is change our problem definition to just predicting playoff outcomes rather than ranking. In addition to these things, exploring other models such as a neural network could prove to be beneficial for this project and other projects alike. And these are the references we used. Thank you for your time, and we hope you enjoyed our project.